Today's topic is digital to the analog converter. So last video I give you the analog to digital conversion. So we use the digital signal for the control. And in this case, we have to install the various AND gate, OR gate, NAND gate to acquire to get the required output digital function. Now in the meantime, you can also change the digital to analog converter because after the computer, the signals are output from the computer is usually in the digital format. So this digital signal need to drive the analog controller. So in this case, we have to convert the digital to the analog converter. So we got the equation for the digital to the analog converter. So VR is equal to VR and B1 2 power minus 1 plus B2 2 power minus 2 plus so etc. Bn 2 power minus n. So this is the equation to the for the digital to the analog conversion. So digital to analog conversion, we use this equation. So V1 VR is equal to VR multiply V1 2 power minus 1 plus V2 2 power minus 2 up to the Bn 2 power minus n. So this is for the digital to the analog conversion. In this case, VR is equal to the analog output voltage. Analog output voltage. And the VI is a reference voltage. And so B1, B2, and Bn are the N bit by V1. So this is the N bit by V1. So B1, B2, and Bn are N bit by V1. So VR is the analog output voltage, VI is the reference voltage. So that we also can write the equation VR is equal to N divided by 2 power N multiplied with the V reference. So equation 2 represents the VR is equal to N divided by 2 power N and multiplied with the V reference. So this is for the N digital to the analog conversion formula. Okay, we saw the one problem. Okay, so this one is we have to firstly what is the problem? What is the output voltage of a 10 bit ADC? So analog to the digital converter, which is a 10 volt reference. Is the input is a 001, 010, 01, 10, 101. So this is the input is 001, 01, 10, 101. So we have to find the analog. So in this case, we have to see how many input. So 001, 0110, 101. So this is the first position. This is the first position. So second position, third position, 4, 5, 6, 7, 8, 9. And the 10. So this is for the position. Position 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the B1 is at 1. So in this case, position 1 will be done at B1. This is a B2, B3, B4, B5, B6, B7, B8, B9, and the B10. So B1 is a 1, B2 is a 0. Bit 3 is 1, bit 4 0, bit 5 1, bit 6 1, bit 7 0, bit 8 is 1, bit 9 is 0, and the bit 10 also 0. So this is for us bit. So we have to use the formula. VR is equal to VR multiply V1 2 power minus 1 plus V2 2 power minus 2 and to the Vn 2 power minus 10. This formula. So we have to use the VR. So VR, so V1 multiply 2 power minus 1 plus B2 multiply 2 power minus 2 and to the Bn multiply 2 power minus n. So VR. So reference voltage VR we already calculate. So reference voltage is at 10 volt. So B1 is at 1 multiply 2 power minus 1. B2 so 0 multiply 2 power minus 2 plus B3 1 multiply 2 power minus 3. The B4, 0 multiply 2 power minus 4. The B5, so 1 multiply 2 power minus 5. The B6, so 1 multiply 2 power minus 6. The B7, 0 multiply 2 power minus 7. The B8, 1 multiply 2 power minus 8. The B9, 0 multiply 2 power minus 9. The B10, 0 multiply 2 power minus 10. So by using the calculator we saw, so that will give us 10 multiply 0.1767528. So that will give us 1.7625284. So this is for us of the out we can calculate by this way. So this is for us 0.0101001. So that's this down. And another one is that we also need to calculate for the 20FH. So we calculate for the 20FH. The 20FH means, so this is the FH is the position 1. So this is for the position 0. Yes, this should be start from 0. B0, B1, B2, B3, B4, 5, 6, 7, 8, 9. So this began as B1, 1, B2 is B0 is 1. But here we use for letter 2 1 minus 1. It doesn't matter. So this one is a 20FH position. So this is 20FH position means that this is a 0 position. X is a 0 position. So this is for the 20FH. So this one is a 0 position. So this is a position 1. This is a position 2. So this is for the this is we calculate for the Hertz decimal system. So Hertz decimal system. So we calculate. So we substitute here. So 20FH. So this formula. So this is equal to 2 multiply 16 squared plus 0 multiply 16 power 1 plus FH is 15 multiply 16 power 0. So by solving this one, you call the thing will be the 527 base 10. And then this one is a B out. B out formula is, so we calculate, so n divided by 2 power n will be less than. So the n is how many? So this is for the n is this is 527 2 power n. So this is the 2 power. How many systems? So 10 digits is 2 power 10. And B reference is 10 volt. So this is a 5.16484. First formula is binary. So binary numbers are we change to the we already given a digit and we change to the output. So we use the formula. B is equal to B1 2 power minus 1, B2 2 power minus 2, up to Bn 2 power minus n.
So there is no B0?
No B0. But this one is different. This one is this one you have to use that formula. B out is equal to n divided by 2 power n into B reference. In this case, Hertz decimal design given 20FH. So 20FH means that FH is a 0 position, and so 2 is a 2 position, and a 0 is a 1 position. So this is 2 multiplied 16 square plus 0 multiplied 16 power 1 plus 15 multiplied 16 power 0. So by solving this one, you got the thing the 527. So this is the 527 in the number. So number 527 divided by 2 power n. So 2 power n means that n is a 10 digits, so 2 power 10. Therefore, so you substitute this formula, so you got the thing 5.16484. So this is the digital to the analog conversion. Okay, now this is for this position here. Then we can also calculate what input is needed to get the 6.5 volt output. So in this output is 6.5 volt. So we have to calculate for the digital number n. So for 6.5 volt output. So we use the equation. V out is equal to n divided by 2 power n into V reference. So V out is we calculate, so this is 6.5. So number of n we don't know the n, so 2 power n is at 2 power 10. By the way, reference voltage is 10 volts. So then you got the N. So then you got the N is equal to 6.5 multiplied 2 power 10 divided by 10. So then you got the base at 665.6 volts. So this is for the 2 by 5, 6.5 volt output, and this will be 65.6 volts. Okay, another one will use output change. So change of the output voltage and reference voltage are related to the formula. The formula is delta VR. Delta VR is the smallest output voltage change is equal to Vn multiplied 2 power minus n. So this is the equation. Delta VR means the smallest change in the output voltage. The smallest output change. And VR is a reference voltage. And there's a Vn, number of bits in the watt. Number of bits in the watt. So the VR is a smallest output change, VR is a reference voltage, and it's a number of bits in the watt. So this is the equation to the relation between the output change, voltage change, and reference voltage and the number of bits. Okay, as of this stage that we're talking about the digital to the analog converter. So when we use a computer control system. So the computer used to produce a control signal in the digital format, and this digital format is converted to the reference. So the VR is equal to we use the formula VR multiplied V1 to power minus 1, V2 to power minus 2, as the Vn to power minus n. So this formula is an equation to calculate the analog voltage depending on the bit. So bit 1, bit 2, bit 3, as the bit n. So this is the VR the analog output voltage, VR reference voltage, V1, V2, V3, Vn are the n bit binary watts. So this is the one equation. If the binary number is given, we have to use the next equation. So we start. But for another formula is the VR is equal to the n divided by 2 power n of V reference. So in this case, this is the n is the H decimal of the s given, we have to use this formula. So first thing is we have to calculate. So 001, 011, 0101. So this one is you write down 001, 011, 0101. So this is a start from the bit 1 to the bit 10. So with the substitute in this formula, VRU V1 to power minus 1, V2 to power minus 2. So then we substitute all bits. So we got the VR. The second one is the 20FH. So FH means this is the H decimal system. So this is normally the H decimal system. We can count from here. This is one. This is a digital to the analog converter. So we can change the digital signal to analog. So this is the equation to calculate the digital to analog converter circuit is VR equal to VR multiplied V1 to power minus 1 plus V2 to power minus 2 plus the up to the Vn to power minus n. So this pure theta. So let's 32 bits what type system we can utilize for the flip-flop. So flip-flop also there's a storage device. It can store the 1 bit of the information. The flip-flop either D or JK is a storage device, and it can capable of storing the 1 bit of the information. So now that 527 bits then. After you got the 527 bits then, we have to use so this is the VR is equal to and divided by 2 power n and then multiplied with the reference. So then n is you can calculate, n is a 527, 2 power n is a 2 power 10, and so. So you call the thing is a 527, 10. 527. So 20 every time, this is a H decimal system. So this is for the zero position. So this is for the first position, and this is for the second position. So the 2 multiplied 16 power 2 plus 0 multiplied 16 power 1 plus f is a, we can calculate f is a 15 into 16 power 0. So you call the thing is a 527, 10. 527 base 10. But after you call the 527 base 10, we have to use the formula. So this is a V out is equal to n divided by 2 power n and then multiply with V reference. So then n is you can calculate, n is a 527, 2 power n is a 2 power 10, and reference voltage is a 10 volt. Then you got the V out, then we do this 5.146484. So this is for us, we can calculate the V out. So if there's a digital binary number is given, you can directly substitute the above formula. So V out is going to be reference multiplied B1, 2 power minus 1 plus B2, 2 power minus 2, up to B and 2 power minus n. So input is given as a binary number, you can use that formula. But the input is given in the octet or the hex decimal. Firstly, you need to change the decimal, and then you have to use the formula. So that this one second program is the B is given in the 20fh. So 20fh is the input. This is given in the hex decimal system. Because the hex decimal system, we firstly need to convert it to the decimal. So the 20fh we use, so 2 is a position 2, 0 is a position 1, x is a position 0. So 2 multiplied 16 square, 0 multiplied 16 power 1, x is a 15 multiplied 16 power 0. So by solving this one, you got a 527. This 527 is similar to the n. So in the place of n, you can substitute the 527. So that we write the formula, V out is equal to n divided by 2 power n multiply V reference. So that in the place of n, you have to write the decimal conversion, and also there's a 2 power n is a number of base 10. So 2 power 10, reference voltage 10. So you got the voltage will use 5.146484. So input 20 is a H decimal, output voltage is the 5.14648, analog voltage coming. So this is for the digital to the analog conversion. Okay, so the final part is some input is needed for the 6.5 volt output. So in this way, output is already given. Output given, so that we calculate V out is equal to n divided by 2 power n and the V reference. So V out is we substitute 6.5. We don't know the n. 2 power 10 multiplied with reference voltage is 10. So from here you got the n. So 6.5 multiplied 2 power 10 divided by 10. So this one you got the resistance 5.6 volts. So this is for the n we can calculate. So we also utilize the analog to the digital conversion. So digital to analog conversion, and then the change in the input voltage can also be related to the change in the output voltage. So that we can calculate the base delta V out is equal to Vn multiplied 2 power minus n. So this formula is the delta V out. It's the smallest output voltage change. Smallest output change. Smallest output change. So Vn means that Vi is a reference voltage. Vi is a reference voltage. And n is a number of bits in a watt. And a number of bits in the watt. So this is the equation. So delta V out is equal to VR multiplied 2 power minus n. So delta V out is the smallest output change, and the VR means the reference voltage, and it's a number of the bits in the watt. So now that we use for the one program, 5 bits, and D is a converter, and 10 volt reference. So 5-bit digital to analog converter with a tempo reference. So that we calculate data Vout equal to VR multiplied 2 power minus n. So that we don't know the data Vout. So reference voltage is a tempo by 2 power minus 5. So that by solving this one, you got the base, that will be 0.3125 bar base. So by the way, you can calculate for the output voltage. This lesson is a digital to the analog converter. So we can change the digital signal to analog.
So the next one will be the determine how many bits in the digital analog converter must to produce the output increment of the 0.04 volt or the less. The reference voltage is 10 volt. So in this case, we have to get the increment 0.04, so delta V equal to 0.04 volt. So we write down the equation VR multiplied 2 power minus n. The 0.04 equal to VR is 10 into 2 power minus n. So in this case, we take the both sides as a log. So the log 0.04 equal to log 10 multiplied 2 power minus n. So the log 0.04 equal to log 10 plus log 2 power minus n. So this is the log 0.04 equal to log 10 plus minus n log 2. So that by solving this one, n is equal to the about 8 bit. So we got like this. And V out then we can calculate. So the VR multiply 2 power minus n. So 10 multiplied 2 power minus 8. So you got the 0.0309064. The next one is a DAC characteristic, digital to the analog converter characteristic. So in this case, a digital input with the A0 to the AN and digital to the analog converter, and then we also provide the data latch. Also that we provide a VR. VR is a reference voltage. So that this reference voltage need to be compared with the input, and then we outputs are when coming out. So the equation are here. So VR to V reference are VR and V out to the input and the reference voltage as well as the input bit and the VR. So that formula V out can be calculated. So therefore, this one will be the A0 to AN input, and then we also provide the VR reference voltage and the data latch. And this is data latch is a logic combine provided, and this is the positive P, negative P ground are this is supply. So therefore, output is an analog output voltage coming out. Power supply is a plus or minus 12 volt to the plus or minus 80 volt is provided. Offset is a DAC that usually implemented with the operational amplifier. Then maybe the typical output offset voltage with a zero input. So this is for the digital to the analog converter circuit diagram. The next one is the data network. Data network is we are comparing the switching and the comparing the data. So the those are data are the provided across by switching. So the requires are switching, and then data can be provided. And then by switching functions, our data will be provided in terms of the voltage, and then we can utilize the operational amplifier, and then we take out the analog output voltage. So this is the data voltage system. And this equation is similar to the problem in the previous problem. You look at the previous problem and solve this one as well. So beyond calculation. And the next one is a microprocessor compatible with digital to analog converter data output port. So in this case, this data output will include the address device, address bar, also the bus interface, and the basic assembly. So this is for the analog to digital converter. So that will be process with the analog signal coming. So we passing through the analog to digital converter, and digital output is coming out, and we provide to the computer. The equation to calculate the analog to digital converter is delta V equal to VR multiply 2 power minus n. So the Vn equal to VR multiply V1 2 power minus 1 plus V2 2 power minus 2 up to the Vn 2 power minus n. This is the data bit, and the V in the V outside relationship. So the VA is an analog voltage and the VI is a reference voltage. V1, V2 to VN is an n bit. So in this case, we do this one problem. Temperature measured by the sensor with the output of the 0.04 degree centigrade. We need to determine require analog to digital reference and the watt side to measure the 0 to 100 degree centigrade with 0.1 degree centigrade resolution. So in this case, that will be the maximum temperature. So VR can be calculated equation. VR equal to maximum temperature degree centigrade multiplied 4 by degree centigrade. So VR equal to maximum temperature. We have to measure up to the 100 degree centigrade so that we can utilize the 100 because of the to measure the 0 to 100. And then, so therefore is the increasement. Output is a 0.02 volt per degree centigrade, so 0.02. So we got the 2 volt. And then write down the equation that are we got resolution multiplied 4 by degree centigrade. So the resolution is that we use the resolution 0.01 degree centigrade resolution multiply with the 4 bar degree centigrade. So 4 bar degree centigrade 0.02. So we substitute and we got the 0.002 volt. And then we also have to calculate the watt size. Watt size is the bit number. Bit number n had to be calculated. Therefore, that we write down the equation. That are we got to VR multiplied 2 power minus n. That are V is that we already calculated 0.002. VI reference voltage is that we also see that we are here reference voltage is the 2 volt. And then we from here we saw the about n, so n we began the about 10 bits. So 10 bits can be calculated. So 10 bit what is required for the resolution. Therefore, we have to find out the delta V. So VR multiplied 2 power minus n. So 2 multiplied 2 power minus 10. So we can call the 0.001950. The next one we find the digital watt the result from the 3.127 volt input to the 5 bits are analog to digital converter. A 5 volt reference, the resolution between the input and output as well. So therefore, then we have to calculate. So that will be the input voltage is here, the 3.127 volt given here, and reference voltage is 5. So the Vn equal to Vr, A1 to power minus 1 plus A2 to power minus 2 up to the A3 to power minus 3. And then the Vn is a 3.127, Vi is 5. So we got the A1 to power minus 1, A2 to power minus 2, A3 to power minus 3, A4 to power minus 4, and the A5 to power minus 5 equal to the 0.6254. So therefore, that we have to find out there's a digital watt. So in this case, 0.5254 multiplied with 2, so you got a 1.2508. So the A1 is a 1. So the 0.2508 is a you take and the multiply with 2, so the 0.05016. In this case, A2 is a 0. And the 0.5016 multiplied 2, so the 1.0032, so A3 is 1. 0.0032 multiplied with 2, so the 0.064, A4 is 0. 0.064 multiplied 2, so 0.0128, so A5 is a 0. So that we write down the equation A1, A2, A3, A4, A5, 2. So the A1 is a 1, A2 is a 0, A3 is a 1, A4 is a 0, and the A5 is 0. Therefore, the output digital Y is a 10100 base 2. We got. The next problem, the input of a 10 bits ABC analog to digital converter with a 2.5 volt reference is a 1.45 volt. What is the hash output? So we have to suppose the output is found to be the 1B H 1B4H. So what is the body input? So in this case, integer part of the accurate output. That we write down the equation. Integer part of the accurate output and bit equal to Vm by Vr multiplied 2 power n. In this case, reference voltage is input voltage is 1.45 volt, and reference voltage is 2.5. So 1.45 divided by 2 power 5, 2. In this case, 10 bits, so 2 power 10. So you got the 593. So this 593 is an analog voltage, so we have to find out the hexadecimal. So the 593 divided by 16, so you got the 37. So this is the quotient is 1. And then 37 divided by 16, so 2. So this is the remainder is a 5. So the 251. So 251H, this is the digital hexadecimal. The next one is a 1BH4. So in this case, we have to find out the input voltage. So the 1BH4 equal to 1 multiplied 16 square plus B is 11. 11 multiplied 16 power 1 and 4 multiplied 16 power 0. So you got the 4364. So the increments are inputs are n equal to Vm by V out multiplied 2 power n. That equation we can calculate. So Vn equal to the increments are n equal to Vm by integer part of the accurate output and bit can be calculated int n equal to Vm by Vr into 2 power n. So the int is 436, Vn is we don't know, and Vr is 2.5, and 2 power 10. So by solving this one, we in this 1.064 454 we can calculate. The next one is the bipolar operation. A bipolar analog to digital converter is the one which accesses the input bipolar voltage for conversion into the appropriate digital output. The normal output is shift by the half the scale so that the all zero correspond to the negative maximum input voltage instead of the zero. So the INTs are integer power of the voltage can be calculated. Signal can be calculated equal to 1 by VR multiplied with Vn plus VR by 2 multiplied by 2 power m. So in this case, our reference voltage 10 volt 8 bit. So if the minus 5 volt is represented at the always zero condition, so determine the one step increment of it. So the data Vn equal to V reference by 2 power n, so the 10 multiplied by 2 power 8, so the 0.0394. So in this case, minus 5 volt is we can utilize or 0.000000002. So the in this case, step means the minus 5 multiplied by 0.039, so that will be the one step. So 4.961, so that in this case, 0.0000001 is the one step coming out. This is the step voltage we can calculate. Similarly, two step is the shift, one shift the chain move, so the minus 5 multiplied by 0.0392 multiplied by 2, and also three steps. So another is a 1 coming out. So that will be minus 5 multiplied by 0.039 multiplied by 3. And the fourth step is a minus 5 multiplied by 0.039 multiplied by 4. So that will be 100. This is the decimal way more. Firstly, we can start from a 1 and then 10 and then 11 and then more 100. This is the ways that we import that digital form. The next problem is what is the hex and the binary output of the bipolar 8-bit analog to digital converter with the 5 volt reference for input of the minus 0.5 volt and the minus 1.5 volt. What input voltage will cause the output 72H? So in this case, we write down the equation. VR equal to 5 and the N equal to 8. So the INT N equal to 1 by VR multiply V in plus of VR by 2 multiply 2 power N. So the in this case, VR is equal to the reference voltage is 5, we substitute. Input voltage is minus 0.85 plus reference voltage is we can got the 5 volt reference of 5 by 2 and 2 power. This is the hex the bit. Now number of bit is 8. So this is 2 power 8. So by this way we start to calculate. So that will be and V is 84 volt we calculate. So this is the way we got. And then after that, we have to calculate. So this will be the hex decimal change. So 84 divided by hex to the 16, 84 divided by 16, so 548. And for the binary, so this is the 84 is converted to the binary. So 2, you got the 1010100. So that will be the binary system. In this case, that will be the 01010100 is a 7-bit. For the output 72H, in this case, 72H we converted to the voltage analog, so the 7 multiplied 16 power 1 plus 2 multiplied 16 power 0, so you got the 114 volt. So the INTs are Vn equal to 1 by VR, Vn plus VR by 2 multiplied 2 power n. So the Vn is a 114, 1 by VR is a 5, Vn is unknown, and the VR is a 5 by 2 into 2 power 8. So we got the Vn is a minus 0.2734 volt we got. So this is where we just better previous ADC system. So if a previous ADC system is a logic counting network included, the function is a conversion of start signal. And then they are connected with digital analog converter. Then this is the comparator. Input voltage is compared with the for reference voltage, and then we have to count the logic counting network. So then we put the subtraction. This is the VR. Also the digital output line. Digital outputs are V0 to P1, P2, and also the this is converting the finish flash. So this is we can see it. So in this case, we have to compare the input voltage Vn, P1 voltage Vf need to be compared. So when the Vn equal to Vn less than the Vr, that will be 2 power minus 1 to the 0. And Va greater than the Vr, so this is 2 power minus 2, so V2 is a 1. This is for the previous ADC converter operation.